the second video on clotting. In this video we're going to look at the coagulation cascade with help of some animations. But first of all, it's worth saying that students generally hate the coagulation cascade. It seems really complicated, and part of the problem is that there's really two ways of looking at coagulation. The first is what happens in the lab or in vitro. So this is basically the intrinsic and extrinsic systems you might have already heard of if you've read about coagulation already. And that's really useful for helping us understand the blood tests which we do for coagulation. The other way of looking at coagulation is what probably happens in real life or in vivo. We're going to look at both of these in the video. Regardless of how you're looking at coagulation cascade, the end goal is the same. We want to create a fibrin mesh. Now, fibrin can only polymerize when its active site is exposed. It comes in an inactive form called fibrinogen, which has a protein block over the active site. To become activated, it needs a protease enzyme to chop off that protein block and reveal its active site. The protease enzyme also has an inactive form, which again has a protein block over the active site, and thus that requires a different protease enzyme to cut off its protein block. In fact, the whole coagulation cascade is just a series of enzymes activating other enzymes, which activate other enzymes, and so on and so forth, until we get a fibrin mesh at the end. First, let's look at the traditional laboratory model for coagulation, which you'll know as the extrinsic and intrinsic pathways. But what do these names actually mean? Well, the extrinsic pathway is triggered by substances found outside of the blood, whereas the intrinsic pathway is triggered entirely by substances found inside or intrinsic to the blood. The extrinsic pathway is very simple. Tissue factor is a membrane protein in subendothelial tissue, and it's not normally exposed to blood. When there's an injury to the vessel, tissue factor is exposed and it binds to factor 7, which is already active in the blood. This complex of tissue factor and factor 7 goes on to activate the common pathway. When we've drawn two arrows joining like this, two factors join together and help each other, and these are called cofactors. The intrinsic pathway is a little bit more complicated. In classical in vitro descriptions of the pathway, kallikrein will be mentioned, as these are thought to be the molecules which help start the pathway. I wouldn't focus on these too much though, they don't really help you to understand the tests, and they probably don't really function much in human physiology. So with the intrinsic pathway, factor 12 is activated. This then activates factor 11. Factor 11 activates factor 9. Factor 9 then joins with its cofactor, 8, and then they go on to activate the common pathway. So it's easy, 12, 11, 9, 8. Now let's look at the common pathway. First part of the common pathway is the activation of factor 10 by either the extrinsic or the intrinsic pathways. Factor 5 is another cofactor. It helps factor 10's activity. Activated factor 10 converts prothrombin into its activated form of thrombin. Thrombin is a really important central molecule here. It's really important physiologically, as we'll go on to find out. Fibrin is a monomer, which loves to stick to other fibrin. The inactivated version, fibrinogen, has bits blocking its sticky ends. These blocks are cut off by thrombin. In our models of how coagulation works in real life, thrombin seems to be of central importance. There seems to be two phases of thrombin production. There's an initiation stage, and then there's an amplification stage, which is about 1 million times bigger in terms of how much thrombin is produced. Let's look at that in detail with an animation. First is the initiation phase, which resembles what we were just talking about as the extrinsic pathway. A vessel injury occurs, and then tissue factor is exposed to blood. Activated 7 joins with it, and together they activate factor 10. Activated factor 10 converts prothrombin to thrombin. Tissue factor pathway inhibitor quickly puts a stop to this initial thrombin-producing burst. Now the amplification phase happens. What we just talked about as the intrinsic pathway is activated at the level of factor 11. The important cofactors are then activated. Factor 8, which joins activated factor 9, produces a complex which together activates factor 10. The other cofactor is factor 5, which is the cofactor for factor 10. Thrombin's central purpose is to convert fibrinogen to fibrin, and this allows it to polymerize. The other cofactor thrombin activates is factor 13, which helps the fibrin mesh to cross-link and becomes even more strong. It can be a bit confusing, so it's worth probably rewinding a bit and looking at it a few times over. To recap, the initiation phase is started by a complex of tissue factor and activated factor 7. Together, these both activate factor 10. This produces a small amount of thrombin because it's short-lived, but that goes on to activate the amplification phase. There's a lot of positive feedback and signal amplification. The intrinsic pathway is activated at the level of factor 11. The cofactors 5, 8, and 13 are activated to help out. Eventually, fibrinogen is activated and a fibrin polymer mesh is formed. But if this process was just left to go on, soon all the blood in our bodies would just turn into one giant clot. So clearly there's something going on to limit coagulation and to break down clots. We'll talk about this in the next video.